No questions? Life is good? All right. Well, let's continue on with our discussion of continuous distributions. So the one we talked about right at the end of class last time was the uniform distribution. I know it's been a little bit. So remember our uniform distribution on an interval from A to B. Zoom in a little bit there. If you've got a length or an interval from A to B and you're uniform on that, your PDF is 1 over the B minus A, the length of the interval. Basically, you're using a uniform density, if you want to think about it from a density perspective. You're using a uniform density over the interval. That's our PDF. We also came up with a formula for the mean, generally speaking, and a formula for the variance. This is there at the bottom. Okay. For any uniform on the interval from A to B. All right. So if we look at the next problem on your sheet, the handout last time, you've got a moment generating function given to you, and it's asking for the different pieces here. What we did not talk about at the end of class last time was how to get the moment generating function for a uniform distribution. So remember that our definition, how do we define moment generating function? By definition, it's what? Good. Expected value of e to the tx. So for if we do a uniform distribution on the interval from A to B, then we would do the integral from A to B of e to the tx and then times 1 over b minus a d t tx, sorry, not dt. Your 1 over b minus a, of course, has no x's in it. The only part that has an x here is the e to the tx part. Antiderivative for that's going to be what? It'll be an e to the tx, and then out in front it'll be a 1 over t, right? Because we're going to undo it, right? And we still have the times 1 over b minus a here, and we'll evaluate that from a to b. So we'll end up with, on top, you'll end up with an e to the bt minus e to the at, and then on bottom you'll have a t times b minus a. So there is your moment generating function for, pardon me, a uniform random variable on the interval from A to B. There is a slight technical thing that we have to worry about here. Remember, I told you back when we started doing moment generating functions, they're only useful if you know that it's defined in an interval around 0. The way I have this written, is it defined as 0? No. Okay. However, and you'll notice how it's written in this particular problem. However, you can do the limit as t approaches 0 and find out this really is equal to 1. You do it that way. Pardon me. So technically, we also need to use that piecewise defined idea and say define the moment generating function at this point to be 1 at 0, so that you can actually talk about it. All right, the reason why I mention it in this case is I want to look at this moment generating function. Does that moment generating function fit this form? And what are the a and the b? 5 and 4, right? The a is 4, the b is 5. Notice it also needs to work on the denominator, right? But 5 minus 4 does give you 1, correct? So what we can do here is recognize immediately from the moment generating function. We recognize that this is the moment generating function of a uniform random variable on the interval from 4 to 5. So rather than working with a derivative and a second derivative to try to figure out expected value of x and variance of x, I recognize that this is a random variable, a uniform random variable instead, based on its moment generating function, and then I can answer expected value of x and variance of x using the properties that we talked about before. So when we did uniform random variable, how do we figure out what the mean is? Yeah, a plus b over 2. So we get 9/2 in this case. It's the midpoint, right? It's the whole idea of being uniform, correct? Okay. And then the variance is what? Yeah, b minus a squared over 12. In this case, our b is 5 and our a is 4, so we just get a 12. So again, we didn't need to go through, I mean, even though we're given the moment generating function, and you could go through and do your first derivative and your second derivative stuff to get to the expected value and the variance, it's much easier to recognize what this is a moment generating function for, right? It's much easier to recognize that and then use our formulas instead. That okay? All right, the last one I think is just also it's easier to think about it in terms of being a uniform distribution, but not necessarily with the formulas, but what the graph looks like, right? So if I think about it this graphically, I would have the interval from 4 to 5. I know I'm going to have a constant PDF over that interval. Where is that height going to be? What would the y coordinate be where that is 1, right? Because it's 1 over b minus a, right? The b minus a here is 5 minus 4. So I would have 1 for my height, correct? We want the probability that you're between 4.2 and 4.7. So what am I really looking for? Relative to the picture, what are we looking for? The area of that rectangle, right? Which is pretty easy to find, isn't it? The height is 1, the width is 1/2. So our probability that x is between 4.2 and 4.7 will just be 1/2. Did it matter that there was a strict inequality for that left endpoint and equal to on the right endpoint? Did it matter? No, because again, in this case, we're doing continuous distributions, right? And then for a continuous distribution, try that again. For a continuous distribution, the probability that you're actually equal to a particular value is always what? 0. So you could have had both of them being less than or equal to, either one of them and not the other one being less than or equal to, or they're both strict inequalities and you would have had the same answer. What does matter? Questions? No one okay? All right. So next one, same kind of concept here. They're asking you to remember the various formulas for things for a uniform distribution. So if it's uniform on the interval from 1 to a, what's the expected value going to be? Yeah, the 1 plus a over 2, good. And the variance will be over 12, good. Now all it's asking you to do is solve an equation, isn't it? What equation are we going to solve? Good, good. So we'll do 1 plus a over 2 equals 6 times a minus 1 squared over 12. Yeah. 6 over 12 is 1/2. Notice there's a 1/2 on the left-hand side as well. So we just get a 1 plus a equals, if we multiply out the top on the other side, you get an a squared minus 2a plus 1. Not cubed. Subtract everything to the right. You get a squared minus 3a equals 0. You can factor out an a. The solutions to that particular equation are 0 and 3. Which one do we want? The 3, right? Because it tells us we want the a to be bigger, right, than 1. So we want that as our solution. That one okay? Uniform distributions, not too bad, right? We have a pretty straightforward PDF. Personally, I think it's a very straightforward PDF. We've got nice formulas for expected value and variance. And typically, if we're doing things with a uniform distribution, it's a lot easier just to think about an area argument than anything else to figure out the probabilities. I wouldn't bother going through the integrals personally, since it's just a constant function. All right. So let's do one more type of problem with the uniform distribution, only because it's going to illustrate a particular idea that we're going to do later on with more complicated distributions. And then we'll talk about a couple of new distributions today towards the end of class. All right, so notice what we're doing here. We've got a random variable. They're telling us that it's uniform on the interval from 0 to 1. And then we're doing a transformation of that variable. Some of you may have had or may be taking data science and doing Monte Carlo simulation. If you talk about Monte Carlo, if you haven't, you can ignore what I'm about to say. But if you talk about Monte Carlo simulation, this is the same kind of idea. Typically, in your on your computer, you can generate a random number between 0 and 1 with a random function, right? But you might not want it to just be uniform between 0 and 1. You might want to transform that into a different type of distribution. Maybe you want to transform it into a normal distribution or some of the other ones that we're going to learn today. But you might want to transform selecting a number between 0 and 1 to some other type of distribution. This process that we're going to talk about right now is this process of being able to do that, transforming one type of distribution into another. Okay. And that's exactly what we're doing, right? We've got this new random variable called w is a function of this y, or as a transformation of the y. Okay? So the way we're going to handle doing these transformations is rather than doing the try to deal directly with the PDF, we're going to start with the CDF, the cumulative distribution function first. Okay. The reason why, hopefully, because remember, what's our relationship between the CDF and the PDF? How do you get, if you start with the CDF, how do you get to the PDF? Or work the other way. If you want to start with a PDF, how do you get to the CDF? What calculus operation do you do? Yeah, so integral from PDF to get you to the CDF. So going from CDF to PDF will do derivative, right? Okay. So that's why we're going to start with our cumulative distribution function. And that's exactly what it says, is to find the distribution function of W, and then we can take the derivative and we'll be able to find its PDF. Okay, that's the idea. All right, so remember how we define our cumulative distribution function. Remember, that is accumulating probability, right? It's the cumulative probability up until a certain point. So we want to calculate the probability of W up until some little w. That's what we're trying to do. Okay. Now, rather than trying to write this as an integral, because we don't have anything to integrate, we're going to just play around with the y, do a substitution and play around with the y, and write this in terms of the distribution function for y. So let's see how that works. We know what w is, pardon me, in terms of y. So I just replace it. So just writing down what w is in terms of y. I know what the distribution function of y, I know what the, I'm sorry, not the distribution of I do, but I know what the distribution of y is, right? They tell us y is uniform on 0, 1, correct? Okay. That means what I want to do with this is solve for y to start with. I know what the distribution of y is, so I'm going to solve for y. To do that, we would subtract the a and divide by the b minus a, correct? Okay, so before we write this down, let's talk about where we started and where we are now. This statement right here is a statement about the cumulative This is a statement about the cumulative distribution function, the CDF of W, right? We transformed that into a statement about the CDF of Y, right? So this is equal to G of W minus A over B minus A, where G of Y is the CDF of capital Y. All right? If this were capital Y is less than or equal to little y, that would be G of Y, isn't it? That's exactly the definition of the distribution function, isn't it? What do we replace little y with? We replace little y with this thing on the right-hand side. Okay? It's just a composition function. All right. This is cool. We're almost done. All right. I now know that my f of w is this same distribution function of y, right? If I want to go from CDF to PDF, what do I do? Derivative, right? If I go from CDF to PDF, we differentiate, right? PDF to CDF, we integrate, right? So if we differentiate both sides, my capital F becomes a little f because we use capital F for CDF, a capital letter for CDF and little letter for PDF. On the right-hand side, I'll write it this way to start with. I'll write it as capital G prime of W minus A over B minus A times 1 over B minus A. Where does this 1 over B minus A come from? We're differentiating with respect to W. Where does this 1 over B minus A come from? Chain rule, right? It's 1 over B minus A times the quantity W minus A, isn't it? So when I differentiate the W minus A, we'll get a 1 over B minus A. All right. This derivative here is the PDF of y. I'll write it as little g. But what kind of distribution does y have in this problem? Uniform on what interval? 0 to 1. So what is g of y in this case? It's just 1, right? If y is uniform on 0, 1, then g of y is just 1, right? So what does this simplify to here that I just circled? 1, because it's always 1, right? All right, so we found the PDF for W. What do we recognize this is the PDF of? It's uniform, right? This is a uniform PDF on what interval? I agree it's uniform. On what interval? It'd be A to B. Let's verify that makes sense. Let's go back up to our function. Zoom out just a smidge. Go back up to our function here. Here's our function, right? Y goes from what? 0 to 1. If y is 0, W is equal to A. And if y is 1, W is equal to B. So it really does range from A to B. Right? You may recognize this form. This pops up in parametric equations, for example. If you wanted to go from one point to another point, the A would be your starting point, the B would be your ending point. You're trying to find the line between those 2 points. And then you let your parameter go from 0 to 1. I know, I try to make connections to other classes that you've taken. What's wrong with me? Right. This okay with what we did? This little technique that we did right here is one we're going to come back to actually here in a minute. Okay, but we're going to do this several times over the course of the semester. But again, this is also important for, like I mentioned before, with Monte Carlo simulation. We start with one function one random variable as a function of a uniform one, and then try to undo the transformation, doing an inverse idea, right? I solved for y. I'm trying to undo the transformation, trying to do an inverse transformation, right? To find the new distribution. And that happens with Monte Carlo simulation if you're trying to get a distribution that's not uniform. Okay. All right. Any questions on that one at all? All right. One more here with a uniform, and then I think we're getting to the next one. Yep, we do. Okay, cool. All right, let's do one more with the uniform distribution. Again, here, I think it's a little bit easier to think about it in terms of areas rather than trying to do any integrals or anything along those lines, personally. Okay. The reason for that is because geometrically, this is a really straightforward idea. My PDF, again, will be constant from 0 to 10. What will the height of my whole rectangle be over that interval from 0 to 10? 1/10, right? Because I need the area to be 1 for that rectangle, correct? If the width is 10, my height better be a 10th to make it an area of 1. Okay. So basically, all we want to do for this one is see if we can convert that inequality statement into something where I can see a rectangle to calculate the area of. Okay. So what do you think I might want to do first to that just playing with the inequality, not worrying about the fact that it says probability. What do you think you might want to do first? Say it again. I would love to be able to cancel out the x. What do I need to do to be able to cancel out the x? Multiply both sides by x. Now, usually, we have to be careful when we do that with inequalities, right? Because if it's positive, we don't flip the inequality, but if it's negative, we do. In this particular instance, can x ever be negative? No, because x has to be between 0 and 10, right? You do have to be careful if it can be negative, and we are going to come back to that idea later in the semester as well. Okay. All right. In any event, multiply both sides by x. Now what do you think you might want to do? if that were an equal sign rather than a greater than sign, what would you do? Yeah, move the 7x over, because what do you want to do now? Factor. Good. I agree. That particular polynomial factors is x minus 2 and times x minus 5. And we want to know when that, now at this point, we should be able to start to translate this over to the picture, right? Where is this equal to 0? 2 and 5, right? Now the problem is, what piece do I need, right? Okay. But notice, and if you've thought about this from a calculus perspective, where you've done increasing and decreasing functions, or when a function is increasing and when a function is decreasing, you broke things up into intervals and checked signs, right? It's essentially the same thing we're doing here. When is this product going to be positive? What interval or intervals are we talking about? 5 to 10 is one of them, right? This one works. Any other interval? And 0 to 2 works, doesn't it? Those are the two intervals that we're interested in. If you're between 0 and 2, both factors are negative, what makes it positive. If you're bigger than 5, both factors are positive, which makes it positive, right? Well, in between, what would you, if you put a number in between 2 and 5, what kind of a product do you get? Do you get positive or negative? Say you plug in 3, what do you get? Negative. I don't want that one. I want it to be positive. I want it to be greater than 0. So I'm in this rectangle or this rectangle. Can you figure out these areas? What's the area of the first rectangle? 1/5, and the second one is 1/2, which is 7/10. You could have also got it from a complement idea, right? I don't want that area. That area is 3/10, and you could have subtracted it from 1. You got the same answer. Is that okay? So notice we transformed our inequality into something that we could read off the picture quickly, and then calculated the areas from that, rather than trying to do some integral piece. I think it's just easier to look at it that way. What questions do you have? I've got a width of 5 and a height of a 10. Okay. This okay? They'll look very happy about it. All right, okay, let's go on to a new type of distribution then. So we've got the setup in the next problem, but we need to do a little bit, we'll talk about the setup of the next problem and talk about what kind of distribution we have. All right, so in this particular setup, it says that we've got calls coming into a switchboard on the average of 2 for every 3 minutes. But notice, rather than counting how many calls come in, it's asking us the waiting time until the first call. Okay. Now, we have a Poisson process. Remember, our Poisson process was something very specific, right? Individual occurrences are independent of each other, and you can chop up your interval into enough pieces that the probability of exactly one occurrence in that small interval is directly proportional to the length of that interval, and you can't have 2 occurrences or more in that interval, right? That Poisson process was very, very specific, right? Basically, what we say with a Poisson process, besides the independence part, is that 2 things can't happen at the exact same time. Okay. All right. So, pardon me. We are doing this in terms of, or sorry, it's asking for waiting time rather than number of occurrences. Well, certainly waiting time is infinitely divisible, right? We can divide up time into any small interval that we would like, right? So this is a continuous random variable, so I can't just, even though it says it's a Poisson process, I can't just assume that I'm using the Poisson PDF, because Poisson is a discrete random variable, right? Poisson counts number of occurrences in a unit time interval, right? This is asking for a waiting time until a first call. Okay, so this is a different idea. All right, so let's see if we can do this generally and then come back and answer the question. Okay, all right. So let's let, I believe your book starts with a W, so I'll do a W. Let's let W be the waiting time until the first occurrence of a Poisson process. Calls coming into a switchboard, people walking into a bank, looking at number of flaws in a roll of aluminum, what have you. I'm going to inspect or wait, calculate the time until the very, very first thing comes in. First call comes in, first customer comes in, first flaw I see. Okay? All those are a waiting idea. Right? So that's what my W is doing. We're going to start with the distribution function and work to get to our PDF. So again, by definition, our distribution function is the probability that capital W is less than or equal to little w. Now, writing it this way is that this is saying that our waiting time is less than or equal to some value. So again, it's the waiting time until the first occurrence. Well, I could have one occurrence up until that time. I could have two occurrences up until that time. I could have 3, 4, 5. That's hard, right? At least I think that's hard, right? So let's convert it to the complement statement. This says that we would do, the complement of this is 1 minus the probability that the waiting time is greater than W. That's something that I can actually think about. Because if my waiting time is greater than W, I can't have any occurrences from time 0 until time W. Right? So this is the same thing as 1 minus the probability of no occurrences in the interval from 0 to W. Well, if W is the waiting time until the first occurrence, and I want the W to be greater than little w, then I didn't have any occurrences at all from 0 up until W for certain. Right? Okay. What kind of process are we doing? A Poisson process, right? Now remember, for Poisson processes, I can scale. We've done the scaling bit, haven't we? We can scale it by length of interval. So instead of being a unit interval here, I have an interval from 0 to W. So I can scale my Poisson process, all right? So let's say that the Poisson process, oops, started to write the word process before I wrote the word Poisson down. Say that the Poisson process has parameter lambda on the interval from 0 to 1. So let's think of 1 as being my unit time interval. okay? Whatever that happens to be. What is the parameter then? If we make the interval from 0 to w the unit length. Rather than 0 to 1, what if we make the interval from 0 to w be the unit length? What's the new parameter? Say it again. W. Yeah, exactly. We multiply, right? Remember, it's directly proportional to the length of the interval, right? We've talked about that before, correct? If we had some of the problems that we did before was if it was 2 occurrences in an hour, we could scale it to 4 occurrences in 2 hours, right? Or 1 occurrence in 30 minutes. We talked about scaling, correct? This is all this is doing is just scaling, okay? We want no occurrences in this unit interval, and this is our new parameter. How do we calculate that using a Poisson distribution? I'm just rewriting the same thing that I had above so I can continue down. How can I write that now? Okay, good. Lambda w all to the 0. Good. Over 0 factorial. Good. Exactly right. Remember, your Poisson PDF is lambda to the x, e to the minus lambda over x factorial. Remember that? That's our Poisson, isn't it? We want 0 occurrences in that unit interval. Again, the unit interval here is 0 to w, so the parameter is lambda w rather than just a lambda, right? And the x value is 0. Lambda w to the 0 is equal to 1. 0 factorial is equal to 1. So now we have a distribution function of 1 minus e to the negative lambda w. Cool. Can we get to the PDF now? How do we get to the PDF? Derivative. When you differentiate, the 1 will go away. You'll bring down a negative lambda. So the negatives will make a positive. You'll get lambda e to the negative lambda w. Okay. So now we have a PDF. Now we can answer questions. Even better, we have the CDF. We can answer questions, right? Okay. Now, we refer to this as an exponential distribution. A lot of times, we will change the lambda or the theta to 1 over lambda this way and write it this way. Okay. This is an exponential distribution with parameter lambda, or parameter theta, I mean. Okay. I've defined it this way. A lot of times, there is a reason why. We'll see why. Okay, we're just defining theta to be the reciprocal of the lambda. It kind of makes sense. Let's think about it this way. If you have 2 occurrences every hour on average, how long would you expect to wait until the first occurrence? If you have 2 per hour, how long on average would you expect to wait for the first occurrence? Half an hour, right? They're related as reciprocal ideas, right? So we're going to come back to that here in a second. That's why we write it this way typically for the exponential. Okay? All right, let's see if we can do this to answer the question. Then we'll come back and gather information about this particular distribution. Okay? All right, so let's go back up here Telephone calls enter at a rate of 2 for every 3 minutes. X is the waiting time until the first call. Okay? All right, so your lambda value, and we'll convert it to a theta here in a second. 2 for every 3 minutes. What's your, if you're going to do waiting time in minutes, what should your lambda be here? What the heck is that? Bird all mad over there? 2/3, good, because we're going to scale our time to minutes here. So our lambda will be 2/3. So our theta will be 3/2. Good. Now notice when we do our PDF, it's going to be 2/3 e to the negative 2x over 3 because your theta is the reciprocal. Okay. There's our PDF. Okay. Now, just like before, we talked about that we could do this with an integral, right? The integral, if we just set this up as a straightforward integral, not worrying about anything except setting it up as an integral, what would the integral look like? We're not going to compute the integral, by the way. What would the integral look like? 2 to infinity, good, of the PDF, right? That's what it would look like. I don't want to do it that way. You can absolutely do it this way. If you don't like the 2 to infinity, I could write it as a complement and do 0 to 2, right? We agree? We could do 0 to 2 instead. I don't like that either, because then I actually have to do an integral. But notice we already came up with, if I scroll back down here, didn't we already come up with the distribution function? Didn't we already come up with it? Why don't I just write it in terms of the distribution function, right? So going back over here, your probability that x is greater than 2 is 1 minus the probability that x is less than or equal to 2. And that's a statement about the CDF, isn't it? We've accumulated probability up until 2. So that's a statement about the CDF, right? Our CDF in this case is what? It's 1 minus e to the negative 2x over 3. Oops, except that my x is a 2 here. Your CDF is, I don't have it written close by. I'll write it down here. Depending on which way you think about it. The theta goes in the denominator, the lambda goes in the numerator, whichever way you want to think about it. Okay. So our theta here was 3/2, lambda is 2/3. We plug in 2 for the x. So I can write this now as e to the negative 4/3 is our answer. No integrals to compute. I already had the CDF, so I don't need to worry about computing an integral here. Makes it a little bit easier, doesn't it? We're going to do more of these, but what questions do you have on this one? Yeah. Say that again. They told me they wanted the x is greater than 2, right? So that's my x value, what goes in here. That's what I'm replacing for the x. The CDF has an x right here. Oh, it had a w in the previous one. That's just whatever name you gave for your variable. When we wrote it down for the CDF earlier, I used the w because that's what the book uses. Most of the time, we'll use an x, so it's going to go in for the x. Whatever name you're given for the random variable. All right. Before we go on with the next problem, let's figure out moment generating function, mean, and variance. Sounds like fun, doesn't it? No? I think it sounds like fun. Let's do it. Okay. All right. We'll do moment generating function first, because again, if I have moment generating function, I can do mean and variance from that, right? Okay. All right. Moment generating function, again, by definition, is what? Good. Expected value of e to the tx, right? Our support for an exponential distribution is 0 to infinity. Again, it's waiting time until first occurrence. So waiting time cannot be negative, right? But it could go on forever. Okay. So we do e to the tx times 1 over theta, e to the minus x over theta. That's our PDF. We can pull, well, I'll pull it out to start with. 1 over theta out in front. We can add our exponents here. Notice that your exponents will have, both of them will have an x in it, right? We'll have a t minus 1 over theta. Get a common denominator, you'd have a theta t minus 1 in that case, right? If you get a common denominator, I'd have to multiply this one by theta over theta, and then factor out the x, or factor out the x and then do it. Doesn't matter which order you do it in. What do you get for an antiderivative? Good. So far, so good? Okay. All right, so now we have to be a little bit careful. Okay. Because the first number I'm gonna plug in is infinity, right? Agreed? Okay. If I'm going to plug in infinity, that's really a limit. If I want this limit to exist, what better to be true about this expression? It needs to be negative, right? So in order for this to exist, my t value needs to be less than 1 over theta. But remember, all we said we had to make sure that happens is that the moment generating function exists in an interval around 0. Doesn't matter how big the interval is, as long as it's an interval. Well, if t is less than 1 over theta, we're still good, right? Because theta is a positive number. We agree? Okay. So we're okay. So when we put in infinity, we'll get 0. When we put in 0, it's going to go in for x. Extra theta. Oh, no. I'm okay there. Put in 0 for, got an extra theta flying around here for some reason. Where is my theta? That theta should not be there. What did I do wrong? This 0 is going to go in for x, so that's going to make that go away. I need this to go away. Where did I go wrong? Let me go back up here. This is certainly the PDF. multiply by e to the tx. Oh, good Lord. I know where it went. I got a common denominator. You know what I forgot to write? The denominator. There's a theta there, isn't there? Okay. Sorry about that. That makes this piece go away. I knew it was wrong because I know what the answer is supposed to be. Why'd you let me get away with that? You gotta start throwing things at me when I make mistakes. Maybe it'll make me stop. Or boo me or something. I need negative feedback, folks. Come on. All right. The reason why the 1 over theta goes away is because I got a theta here in the denominator, don't I? We divided by this theta t minus 1 here, correct? To adjust for the ones on top. I would also multiply by a theta on top, which would cancel that one. Okay. So the 1 over theta is going to go away. So when we put in infinity, we get 0. We already said that. When we put in 0, you'll get 1 over theta t minus 1. I'll distribute the negative sign through the denominator. You get 1 over 1 minus theta t. And again, we need our t to be less than 1 over theta for that to exist. Otherwise, it goes off to infinity. But this is your moment generating function. It's a nice moment generating function, isn't it? At least I think it's a nice moment generating function. Okay. It's also easy to differentiate. Right? Okay. So now we have the moment generating function. To figure out the mean, we'll take the derivative. This is just 1 minus theta t to the negative 1. What's its derivative? And then times another negative theta, right? Yep. So you'll have negative 1 minus theta t to the negative 2 times a negative theta. Chain rule, right? Again, how do we find the mean using the moment generating function? Plug in 0, good. What do you get when you put in 0? We get theta, don't we? This is why by the way, this is why we write the parameter for the exponential function, exponential distribution in terms of the theta. So the mean comes out to just be theta, right? For variance, we need to worry about second derivative. What is the second derivative going to be? I'd work off of this one here. I'll have negative 2 theta, right? Times a 1 minus theta t to the negative 3, and then times another negative theta, right? So we end up with 2 theta squared over 1 minus theta t to the third. How do we find the variance using this? Yes, put in 0 and then subtract the mean squared, right? What do you get when you plug in 0? Two theta squared, good. The mean was theta, so we get theta squared, and we just end up with theta squared when we're done. All right. So for exponential distribution, the mean is theta, the variance is theta squared. A little bit different than what we had for Poisson, right? For Poisson, what was the mean and the variance for both? What was both the mean and the variance equal to? Lambda, right? So it's a little bit different for exponential, even though they're related with the Poisson process. All right, yes. Say that again. Well, so the key word from the question that tells us about using exponential is the fact that we're waiting time until the first occurrence. It's the waiting time part. All right. So going back now to this problem that we were asked about, we have an exponential distribution with a mean of 20. So the theta is 20. That's why it's telling us the mean is 20. I want to talk about these three parts to start with, but not worrying about doing them as integrals. Do them in terms of the distribution function. Okay? First, what would the distribution function be in this case? Not the PDF, but the CDF. What would it be? Good. 1 minus e to the negative x over 20. Okay. Before we do A or C, let's do B. How would I rewrite B in terms of the distribution function? Good. 1 minus to flip it around, right? And then this is the distribution function at 30, isn't it? We agree? So when you're done, you should get e to the negative 3 halves there. That looks like one we did earlier, doesn't it? When we did the probability that x was greater than 2, we flipped it around. Are we okay with part B? I did that one first because it looked like one we already did. Okay. All right, let's talk about A. Before we talk about A, the part that I just circled in red, or I guess rectangled in red, what probability does that represent again? Just the part that I did in red. What probability does that represent? Everything up to 30, right? So looking at A, how could I use that to help me compute A? Say it again. Yeah, you can do the probability that x is less than 30 and subtract off the part you don't want, right? I want between 10 and 30. I could calculate everything up to 30 and then subtract off the part that I don't want, that's up to 10, right? The first part is f of 30. Does it matter there's no equal sign there? Technically, with the distribution function, it's equal to, right? But do I care about equal to as far as continuous distributions go? No. The next part, like Trey said, it's f of 10, right? And now I just need to plug it in. F of 30 is 1 minus e to the negative 30 over 20. F of 10 is 1 minus e to the negative 10 over 20. And if you feel like you're in the mood to simplify, you get e to the negative 1/2 minus e to the negative 3/2. That part okay? How about C here? That's a conditional. Oops. With the probability that x is bigger than 40, given that x is bigger than 10. Conditional probability formula says what? The probability of the intersection over probability of the given. Can we simplify the intersection a little bit to help us figure out the value of the top before we start going off on our way to calculate it? It's just x is greater than 40, right? If you're greater than 10 and greater than 40 at the same time, it has to be greater than 40, doesn't it? And now, can you rewrite these in terms of the CDF again? Yeah, but probably it's less than or equal to 40, so I'll just go ahead and write it as f of 40, right? Over 1 minus f of 10. Right, okay? So then, if you go through and simplify, that'll be e to the negative 2 over e to the negative 1/2. So simplify to e to the negative 3/2. Did we see that answer before somewhere? Yeah, we did, didn't we? So up here is the probability that was greater than 30, didn't we? Do you see any relationship between 30 and 40 and 10? Can you get 30 out of 40 and 10? What do you need to do? Subtract them, right? So this is actually a property of the exponential function. It's referred to as the memoryless property. If you know that you've gone out A units and you want to go out another B units, that's the same as the probability that you just went out B units. That's what's called the memoryless property. I don't know why I have a hard time saying that word. It's memory with less on the end, but I put it all together, I have a hard time saying it. The idea is that with an exponential, if you think about what these exponential PDFs look like, by the way, they start here at 1 over theta, and then they just decrease all the time this way. Oh, hey, not like that. Like that, right? That's what the graph looks like. Okay. Basically, it basically says that if you start at some other point, it looks exactly the same. Has the same kind of shape. Okay. Basically, you're just kind of zooming in a little bit. So if you, basically, if you have something with an exponential distribution, if you know that you last 2 units, the probability that you last up until 5, or at least 5, is the same that way the same as if you would have just lasted 3 to start with. The first two units didn't matter. Is essentially what that says. It's just a property of the distribution. It's not. It's an interesting property, but it's not something that we'll focus a lot on. Last part we should be able to answer pretty quickly. What's the variance? 400. Good. And the moment generating function will be? Good. Yep, exactly. That one okay? All right. Let's do the next one here. This was a little bit different because it's one of those actuarial exam practice problems. And one of the big things about actuarial exams is it's a vocabulary test too, as much as it is a math test. Says the time until failure of a component in an electronic device has a median of 4 hours. It's an exponential distribution with a median of 4 hours. And it wants you to calculate the probability that it will work without failing for at least 5 hours. Well, the for at least 5 hours tells us that we want to do the probability that the x is greater than or equal to 5, right? We agree with that part? We would write this in terms of the complement and then use the CDF part. So we'd have 1 minus f of 5. That part's just like the other parts we did before, isn't it? Not any different. And as soon as I figure out what the theta is, I can answer the f of 5, right? Because this will be 1 minus e to the minus x over theta, or just e to the negative x over theta. Whoops, not x, 5, right? Whatever the theta is, that's how we would compute it, isn't it? Is the theta 4? No. What would it have to say for the theta to be 4? Mean, not median, right? We agree? Okay. So median is a percentile idea, right? So for the median, if M is the median, then what would I get when I plug the median value into the distribution function? What should I get out if it's the median? 0.5, right? It's the thing that splits the distribution in half by probability, correct? So basically we have an equation to solve, don't we? Okay. All right. So in this case, we know the median is 4, right? So we know that f of 4 should be 1/2. F of 4 is 1 minus e to the negative 4 over theta. Now we just need to solve for theta. Right? I don't know what the theta is, but I know that when I plug in 4 into the distribution function, I'm supposed to get out 1/2. Well, if we rearrange our equation, we'll get e to the negative 4 over theta equals 1/2. Take the log of both sides to get rid of your e. Oops. Pardon me. We would get what? Negative. I need to multiply by theta and divide by natural log of 1/2. Right, I got to multiply both sides by theta and then divide by the natural log of 1/2. I can make that look a little bit prettier. I can put the negative with my log. Because it's -1, right? So I can put it on the top or put it on the bottom. I can put it with the log. But if I have a number out in front of the log, what can you do with it? Make it an exponent, so I get 1/2 to the -1. What is 1/2 to the -1 equal to? 2. So I can rewrite this as 4 over log of 2. By the way, this will work for any exponential function, by the way. This gives you a formula for the median. This was the median value, isn't it? Right? So your median, for any exponential, your median is theta times the natural log of 2. That's the relationship between the two. Okay. All right, so going back up here, I now know what the theta is. There's a lot of fractions up there, right? The -5 divided by 4 divided by the natural log of 2. What? That looks like a good problem for a calculator to give you an approximation. Was the process okay? Anytime that you would be being asked about a percentile for an exponential distribution, it's an equation to solve, right? This is whatever the percentile value is here. Right? So if it said 30th percentile, you'd put 0.3 there. If it said 80th percentile, you'd put 0.8 there. is always going to be an equation to solve. That one okay? All right. All right, so there's a couple other practice ones here. Notice the next one even says about percentiles, right? Okay. Let me go down here real quick. There's a couple other problems here with exponentials. I want to do, not that one. Here we go. One with us telephone calls again. Notice that this one, rather than saying x is a waiting time until the first call, this is x is a waiting time until the 10th call. A little bit different, right? This is a clue that you're using what's referred to as a gamma distribution. Okay. Gamma distributions have two parameters. This theta is the same theta as your exponential distribution. Okay. Doesn't matter what that is. That's your same theta as the exponential distribution. Okay. This is your number of occurrences. Now, in this case, it says 10th occurrence. So your alpha would be 10. Generally speaking, though, alpha doesn't have to be an integer. It depends on what you're trying to model with the distribution function. Your alpha could be 7.5. It could be square root of 2. Okay, it could be any value you want it to be. All right. I'm going to write down what the PDF is. Well, we will not write down the distribution function. Okay. Here's what the PDF looks like. In the numerator, we'll talk about where these come from next time. I just wanted to get the PDF down so you can see what it looks like. You get an alpha, x to the alpha minus 1. So notice that if your alpha is 1, this should be an exponential distribution. Okay. So you get x to the alpha minus 1, e to the minus x over theta. That looks like an exponential distribution. Also in the denominator, you get a theta to the alpha. And then out in front, we get something that's referred to as the gamma function. And we haven't talked about the gamma function. The gamma function is pretty cool. At least I think it's pretty cool. Okay. So your gamma function, if I use a different letter for a variable here, your gamma of alpha is the value of this integral. I believe I have we're almost out of time here. I believe I have a video about the gamma function hosted on Moodle. But here's the cool property of the gamma function. You can, using integration by parts, you can prove that gamma of alpha is the same thing as alpha minus 1 times gamma of alpha minus 1. There's a recursive formula here. This should remind you of a certain type of function. What function does it remind you of? I'll write in the next one. This would be alpha minus 1 times alpha minus 2, gamma of alpha minus 2. It also reminds you of a factorial, right? And that's actually true. If alpha is an integer, then gamma of alpha is alpha minus 1 factorial. What's cool about this is it lets you define factorials for fractions or non-integers. So in particular, when we'll do this next time, because it's fun, 1/2 factorial is square root of pi over 2. Square root of pi over 2. That's a kind of a fun fact. Well, at least I think it's a fun fact. Okay. All right. We'll talk about why that is true later. But anyway, we'll do some problems with a gamma distribution. We'll talk about a special type of gamma distribution next time, referred to as the chi-squared distribution, which is exceptionally important in statistics. So, anyway, have a good one. We will see you on Thursday. Don't forget we have a test next Tuesday, too. Yeah, next Tuesday we have a test. I know. It's exciting. You get to show me what you know. Okay. All right. Have a good one.